Please join me in welcoming Mr. Alan Yan, Systems Engineer at Valley Tech Systems, Inc. The topic of demonstration is Valley Tech Systems Active Nozzle Propulsion System Technology. The company will have 20 minutes to demonstrate their technology, followed by a 10-minute Q&A session. And when you're ready, we will start the clock.
Okay. Thank you. As mentioned, my name is Alan Yan, Systems Engineer at Valley Tech Systems. I'm joined here today by Russ Carlson, Vice President of the Aerospace Division, who is in the audience today. And today I will be presenting information about our active nozzle propulsion technology in support of the X-Tech Search 2.0. Quick outline of today's summary. Start off with just a quick program summary. Go into the significance of the innovation and benefits of the technology. Go into a little information about our prototype design that we put together for this demonstration. Show results from our hot fire tests, and then go into information about our path forward and commercialization plans. So one big thing to note about these charts is that they're labeled non-proprietary and unclassified, so that means we had to scrub them pretty heavily for this presentation. The technology is born from the Missile Defense Agency. Valley Tech Systems has been working with it for the past 12 years or so, and we've made some pretty big breakthroughs in the past few years. So this technology is very unique to the United States, and I think everyone can understand that we want to keep it that way as well. So starting off with program summary, just very generically, what are the benefits of the technology? In this presentation, I'll show that this is applicable to two modernization topics, the first being long-range precision fires, and the second being air and missile defense. What we're bringing to the table is controllable solid propellant propulsion, and the key word here is controllable. So that's a very loaded term. I could go and discuss that for hours, and I'll slowly define that in this presentation. Ultimately, what that does, though, it allows for very flexible mission engagements. And in some of the applications, we're seeing that we can increase range by over 67% and increase maneuverability by over 70%. So those are fairly big numbers. In consideration of cost, acquisition, and transition time, we're looking for a relatively simple screw-in upgrade for existing systems. So you have something that you're deployed already. We want to pop the nozzle off, put our system in, and boom, you're pretty much ready to go. We're enabling that through lots of mature technology. So over the years, we've matured our component technology to TRL4 at a minimum. We're also bringing a lot of state-of-the-art control algorithms and software technology, as well as a small patent portfolio that leverages, again, lots of SBI data rights and 12 years of DoD investment. Having said that, as a result of this demonstration, we actually realized that cost is a huge issue for the Army. And so we came up with a very clever way to kind of get around the precision requirements that is typically needed for controllable solid propulsion. So that may be a new patent that we're going to look at after this, or we may just keep it proprietary depending on how things go. Some of the major milestones, I would like to think that we got a lot done in 6 months. So first thing we did was after we won, we got on the phone with our commercialization partner, had a technical interchange meeting, spoke with them, and had a kickoff meeting to kind of strategize what we're going to do and how we're going to approach this. Had a systems requirements review using input from our partner, went into concept design, detailed design, performed the hot fire tests, and all of that will be covered in today's AUSA conference presentation. Major accomplishments, so big thing is, again, we were able to successfully demonstrate a single-axis hot thrust or hot fire test. This test mitigated a lot of the major risks that we were carrying into this at the beginning, and we're confidently able to advertise that we got the prototype up to TRL4. So there's a difference between component and system. So we got the system all the way up to TRL4. That's a lot harder. And then as a part of the judging process last time, one of the judges was so interested, he actually got us in touch with the CDCC in Picatinny, New Jersey, and we actually started talking with them, and we came up with a spin-off application that pretty much uses the same technology applied to an artillery application. On top of that, we've been talking a lot to our commercialization partners, both within the prime contractors and the government offices, and I'll go over that as well. So starting off, significance of the innovation, problem statement. First three columns are just public sources. These are various news articles and government reports regarding how our foreign adversaries have started upgrading all the weapon systems. And in a nutshell, they can outreach us. Very simply put, they can shoot us and we cannot shoot them back. That's the basic issue. So for what it's worth, many years prior, U.S. Department of Defense started looking at modernizing pretty much all branches of the military. So in the Army specifically, it looks like they were prioritizing long-range precision fires as the first one. That being defined as capabilities, including munitions that restore Army dominance in range, lethality, and target acquisition. So Valley Tech Systems Technology, we address all 3 bullet points of that, and then on top of that, air and missile defense. So what is Valley Tech Systems Technology? This is a little tricky chart here. But when we first pitched this idea, we were initially looking at a 2.75-inch rocket motor. So this is actually something that's deployed by the military already. This is called the Advanced Precision Kill Weapon System. What they have in green here is a warhead. Gray is a smart guidance and control system. And then this white and gold section is, for lack of a better term, a dumb rocket motor. You light it, it goes, and it does its thing. So what Valley Tech Systems wanted to do was take that dumb nozzle and replace it with a smart nozzle. So you essentially get a smart rocket motor from end to end. And this is just a teaser of our prototype that we came up with, and hard to show, but it is a screw-in capability. So you can theoretically take off the dumb nozzle, put in the smart nozzle, and there you have it. So conceptually, what can we do with this? This is a sample application shown for an air-to-surface engagement. And some of the things, the letters here correspond to this diagram here. And what we're trying to do in this engagement is, say, a non-line of sight engagement. So say you have to shoot over a building or around a building or over a mountain or something, but you can't see the target and they're very far away and you still want to hit them. So the first thing you may have to do after you shoot it out of in this case, a helicopter, is you have to do a high G turn, kind of really quickly go up. Give yourself a quick boost to make sure you have enough energy to go over your obstacle. And then steps D is the low-level sustain. So this is where our technology enables the long range. But the analogy that I like to use is if you're driving in your car on the highway, you can either drive at like a steady 60 miles per hour and just kind of cruise to your destination. Your gas mileage is probably going to be pretty good the whole way. Or the other way is you can just floor it and drive like 120 miles an hour, but you're going to run out of gas really quickly. So ours, we optimize for the lower speed. We can optimize to our flight and drag profile. And that's how we get a lot of increased range. As you near your target, that's when you want to start like steering. You can kind of open up your eyes, start looking at the target, point at them precisely. And then at the very end, what you can do to increase lethality is give yourself a really kick boost, or give yourself another boost at the end. So the analogy there would be, say, like getting hit by a baseball thrown by a little league pitcher. It might sting if you get hit by one of them. But for a professional player, if you were to throw a ball at you at 100 miles per hour, that's going to hurt a lot more. So that's why you want that terminal boost to really give yourself additional kinetic energy at the very end there. Next slide. This is a similar graphic that we put together for Picatinny, New Jersey. So they had an artillery application. And this, again, is pretty much the same thing, but our technology is scalable to artillery. And overall, we can enhance range, target acquisition, and lethality. Next slide is an application for air and missile defense. In this one, we've been talking to Redstone Arsenal, where they're looking to upgrade their lower tier missile defense. So another deployed Army system, and we're looking to just upgrade it by applying our technology. What they want to do, this one's markedly different, but it still leverages a lot of our technology. First thing you want to do is a very large turnover event. Normally, you're shooting a little straight upward. You mean turn yourself to you're sort of close to the target. And then this idle part is actually the hard part. So there's not a lot of companies that can do this efficiently, but our technology is very good for that. So idle, this is again another aspect of the controllable part, and this is kind of where we excel. And then at the very end, once you're very close to your target, you may be off by just a little bit, so you have to turn it back on and then make very sudden maneuvers to correct yourself at endgame. Compared to conventional fin control systems, fin control can only get you so much because you're limited by aerodynamic forces. Whereas with our system, you have thrust vector control, so you can get a lot more. So the kill box is a lot bigger with our system as well. So overall, increased range and target, or increased lethality and target acquisition. So quantitatively, how much will this help long-range precision fires? The chart in the top left is just to kind of show you that we actually did the work. We ran trajectories for a variety of cases. So top section here is for the static nozzle, the dumb nozzle, and then lower images here for the active nozzles. When we simplify all that data, we got these two charts here. So bottom left corner, we looked at turning radius. So in some applications, some of the missions, there's actually times where you may actually imagine there's like a bogey following you, you're in an aircraft, and you actually want to try and shoot the enemy while they're behind you. So turning radius, in this case, since we're using thrust vector control, we can turn a lot faster than something with the fin control. Fin control is limited by aerodynamic forces, stall angles, stuff like that. So with aerodynamic, you're going to go something really wide. You may miss them. With thrust vector control, you can almost turn immediately and get them right when they're right behind you. Quantitatively, we're looking at about a 70% reduction there. And then in terms of range, we also crunched some numbers. Blue is the baseline for the application that we looked at. Gray is what we had quoted initially during the phase 2 pitches. We're eyeballing about 45% increase in range. And then based on our hot fire tests, we actually took what we learned from our hot fire tests, put it back in our model, reran the numbers, and we're now actually, we are able to squeeze another 15% or so performance out of that. So now we're up to about 70% increase in range, down to about 67% at some engagement angles. So all things considered, very enabling technology accomplished by thrust vector control, deep throttling, and drag elimination. So there's the three main enabling technologies that we bring. Very broadly, some other overall benefits of VTX technology. So there's 5 major areas that we looked at. Mission flexibility, again, the keywords are active controllable propulsion. And if you were to try to simplify it, you can consider that, or you can define it as continuous throttling, or in some cases, extinguishable and reignitable operation. Overall, that'll give you increased operation time, and when you combine it with our flexible on-demand thrust amplitude capability, that gives you options for air-to-air, air-to-surface, surface-to-air, and surface-to-surface engagements. On top of that, we can operate in space, because this is actually where that technology was born from. So pretty much anything you can think of, we can probably accomplish. We use a lot of state-of-the-art materials and manufacturing methods. This gives you very high thrust-capable systems, which also shrinks down everything in overall size. In sensitive munitions, our preferred propellant is kind of what they call in industry a wooden round propellant. So it's very inert, it's very safe, it's very easy for the warfighter to be around. So you can just drop it on the ground, you don't have to worry about it blowing up on you. MIL standard 1901 compliance, that's kind of MIL standard for like some very high-end stuff. Performance, all of that is there. We have high accuracy thrusters, hot running materials, advanced insulators, and thermal coatings. And then life cycle cost is another big one that we're targeting. So again, key here is a drop-in upgrade system. So screw it out, screw it back in, low cost, rapid transition opportunity. Affordable through use of innovative materials, solid propellant maintenance, safety, and storage. And then, as kind of mentioned previously, that unique workaround high geometric tolerancing, which may or may not be patentable. So where is this technology going? Within the DoD, we work with quite a few branches. So we've worked extensively with the Missile Defense Agency, working on ballistic missile defense upgrades. Over the past couple of years, we've started working some of the hypersonic missile defense areas. Within the Air Force, they're looking at us for a ground-based strategic deterrent upgrade. Navy, same thing, Navy strategic missiles. And then within the Army, what we've identified so far is the lower tier missile defense upgrade, the 2.75-inch rocket motor upgrade, which is what this tech presentation is about. We were introduced to the strategic long-range cannon artillery application, and then we actually ran into someone on the exhibition halls where we actually may be able to apply this to a scramjet type application as well for the Army. So quite a few things for the Army on top of the existing branches that we work with. Additionally, within the past couple of months, DARPA actually approached us and started looking at us for the next generation air-to-air missile application. So all around, a lot of potential, a lot of insertion opportunities. Capstone demonstration prototype design. So we went through a very extensive engineering design process for all this. In terms of the VTS engineering capabilities, the Aerospace Division is about 10 people strong. We bring about 12 years of SPR data rights and a lot of in-house and commercially available analysis capabilities. On top of that, we have 2 patents on our technology, as well as 2 patents pending. And cumulatively, we have well over 100 years of engineering capability. And we're familiar with all the way from concept all the way to actually delivering hardware to our customer. Engineering process started off with a requirements review. So we talked to our commercialization partner, got some preliminary input from them, and then put that all into here. So we looked at everything from performance, environment, costs, life cycle, reliability. All of that was in our trade space. Went through preliminary design. So I myself did a lot of the performance modeling and system sizing. Worked with the mechanical engineers to generate an actual concept, which is, again, teaser shown there. On top of that, we did a lot of analysis to make sure that all aspects of the design were covered. And then on top of that, we looked at all the risks, ranked them, and came up with appropriate mitigation plans for that. After all that, we actually fabricated some custom hardware and went into a hot fire test with all this. So to summarize the test, though, lots of good things happened. The major risks that we burned are highlighted or bolded. So one major thing was scaling it down to 3-inch diameter. So it's 3-inch diameter. We're trying to do a lot in that small amount of volume. We were able to do that very well. Data was collected, nothing funny happened. Thrust was collected, and we put that again into our modeling to squeeze out that extra 15%. Successful ignition, performance within desired performance bounds, videos and photos captured. So this black box is a video, which I'll show momentarily. No jamming, clogging, or excessive ablation. Thermal margins are good. Thermal shock survivability. No combustion instability. That was my biggest concern, at least. And then ballistics verified. So can we try to play that video momentarily? So this is just a snippet of it. This is only a small fraction. The real test was many times longer. And again, for sensitivity reasons, I can't show the whole thing and everything that happened or the exact data, but we can show you afterward if you want to. So overall, lots of risks were burned, which is a lead into my next chart. Where do we go from here? If we look at risk rankings at the beginning of the program, we had quite a few yellows. There were quite a few things that we were worried about. The hot fire test brought everything down in the green. If we look at it from a technology readiness level definition, I can very confidently say that we're at TRL4. This was a component validation in a laboratory environment. Our commercialization partners kind of waiting to see what happens after this competition pitch. So if this domino falls, then we would actively engage them. We would get their attention a lot more. And we would push to do a prototype flight demonstration of this hardware. So combined with VTS's high technology already and their capabilities, we can definitely get to a flight within TRL5 or TRL6 within pretty quickly. Overall, in terms of acquisition, if we got the go-ahead to just go ahead and deploy this to some system, we're confident that, again, with our partnership, we can get to actual TRL9 within 2.5 to 4 years. And transition plan. So unfortunately, I don't name any of our prime partners for sensitivity reasons, but I do identify some of our government sponsors in our various branches. So Missile Defense Agency, this is probably our most mature customer. We've been working with them for many years. Within the ballistic missile defense realm, we actually have a test experiment or a flight demonstration happening about this time next year. So we've got both a prime contractor and a government sponsor working with us. Hypersonic missile defense has already gotten a lot of interest out of this. The Air Force, I think we're doing hover tests for them in about a year as well. Navy, we're doing very well. That's all I can say there. And then the Army, for the lower tier missile defense, we're working with Redstone. We're covered there. 2.75-inch rocket motor upgrade. We're waiting for X-Tech to see what happens. And then strategic long-range cannon. We submitted a white paper a few months ago, and we're waiting to hear back what happens about that. But we're very excited about that opportunity. And then DARPA, this is a very new initiative. Haven't made much progress there, but we'll be working it. And then final chart, just to kind of mention commercial applications that we have. So this isn't purely just DoD. Many years back, we had found an application within the oil and gas industry. We actually had teaming agreements, partnerships, and we even had a patent issued for support of one of these applications. Only problem being the oil industry kind of collapsed, so that kind of fell out from under us. Related to that would have been mining. So again, we're just waiting for the opportunity for it to be economically viable again, but we do have ideas for how to transition this into the commercial world. And these are two very big industries, so this is like 9 figures, 10 figures sustainment if we were to get that. And with that, I conclude my presentation.
To switch the nozzle from a dumb nozzle to the smart nozzle, what kind of weight difference how much weight difference is the smart nozzle?
There is. Do note that it was accounted for in the flight ballistic modeling, though. So I don't think it's appropriate to actually quote the number, but it was a part of this analysis.
Okay.
But it will go up, I agree.
The video that you showed, we saw, just kind of an ignition and then it sort of extinguishes. Could you be more specific about what you did verify in terms of revectoring and vector control and those sorts of things?
It doesn't extinguish, it just kind of blacks out. And then thrust vector control is what we could not demonstrate since this was only a single axis test. So we were initially going to do full 3 axes. Due to cost and time, we can only do 1 axis. So we did not verify thrust vector control, but we got throttling.
Do you have any data on nozzle ablation when you're actually doing thrust vectoring, or is that outside the scope of what you demonstrated?
Most of our materials don't really ablate. For this one, it actually did, so that was part of our database. That was part of the lessons learned that we got out of this technology demonstration.
So you talked about the thrust vector control, the de-throttling, and the third technical component. Which do you feel is the most challenging for you to try to overcome in terms of demonstrating the full capability?
Definitely range, throttling, and I kind of hinted towards it, but extinguishment and reignition, that's another key aspect of our technology. And that's the part that no one else can really do, so that's what Valitech brings to the party.
And you talked about the intensity of munition, so this will be propellant agnostic in the end state, or do you, okay.
Propellant agnostic.
Challenges? Again, some of the applications you showed, it seemed like the burn time was relatively short. Do you see any problems going to longer burn time, longer duration at higher temperatures, just in the integrity of the structure that you built?
That's all a part of our engineering capabilities. We work a lot with hot running materials and advanced insulators.
So how long was your test burn compared to a typical flight profile?
Order of magnitude higher. That's about all I can say.
So as you move to the smart throttle, are there hardening concerns in terms of being able to security against compromise or integrity? Someone, how do you control the dynamics of what you're?
I don't see how it could be compromised. That's where our commercialization partner would help out a lot. They'd be able to ruggedize some of the communications and control systems.
Like things, okay.
Any other questions? For the existing systems that you showed and talked about, non-extended range cannon, do you envision this material or your modified rounds having the same form, fit, and function with the, say, the 19-shot rocket pod or the 155 howitzer? Or do you envision, or can you share with us at all how that would integrate to those existing platforms?
Form and fit would definitely be the same. It's not going to be a screw and upgrade though. That's going to take a lot more work it's pretty much going to be a custom artillery round, but we're still targeting the standard 155 millimeter. I think that's the howitzer diameter.
So your TRL forge a component level in terms of the ability to scale up manufacturing. I'm assuming they're using mostly COTS items or other. How's
It comes from our many years of experience. We've developed those materials. We work with it extensively. We're comfortable with it.
Have you performed IG testing in your collaboration with Picatinny?
Nope. That was part of our white paper. That's pretty much the first thing we'll be doing with them, high-G survivability.
How do you handle the very high rates of acceleration of spin when you're dealing with long-range artillery shell? I mean, many orders of magnitude more associated with missile systems.
We would love a contract to answer that question.
Well, my company is one of several contractors to Picatinny Arsenal working on extended range ammunition. Let's talk about that.
Okay. We need to talk then.
Any other questions? Okay.
Thank you.